So today I'm going to talk about an important result from extremal set theory called the Redo sunflower lemma. To state it, we first need a definition of a sunflower. A collection of sets A1, etc. AR is an R sunflower if there exists some set X such that AI intersection AJ is equal to X for any I not equal to J. So graphically this looks like a center X and many petals going out of it are petals which are AI minus X. So what do we want to know about our sunflowers? We basically want to know how many sets in a family guarantee the existence of an R sunflower. We need to be a little bit more precise, and mostly we need to fix the uniformity of a family. So let us define the following quantity. F of k r is the maximum of the size of a family of sets F such that all sets in F are of size k and F has no R sunflower. Basically, once our family has size bigger than F of kr, and all sets in our family have size k, then we can guarantee an existence of such a structure. And these structures are extremely useful in different parts of combinatorics and computer science. So the basic result about it is this Radu sunflower lemma, which states the following bound, upper bound on F of kr. It is at most k factorial times r minus 1 to the power k. And this is the upper bound. It is believed to be constant times r to the k, but yeah, and also there has been some very important recent improvement of this bound, but for today we're concerned only with this simple upper bound. How does the proof go? The proof goes by induction. On k. So note that the case k equals 1 is very easy. Basically what we say is that whenever our family has size r or bigger, and it is a family of singletons, then we have an R sunflower. That's obvious because it has R pairwise distinct singletons. All of them have like any two of them have empty intersection, and on this figure here we'll just have an empty center X and singletons as petals. Empty X is allowed. So this case is trivial. So now we want to pass from k minus 1 to k. So take f with no r sunflower and all sets of size k. Let A1, etc., AS be a maximal collection of pairwise disjoint sets in F. Well, note that S is at most R minus 1, because otherwise A1, etc., AS would be already an R sunflower or even a bigger sunflower. So this immediately implies that the union of these S sets has cardinality at most k times R minus 1. From here we see that there exists X, an element in this union, such that, and let me write the following thing, f of x has size at least that of f divided by k times r minus 1, where f of x is simply the family of all sets from F that contain X, with a slight technicality, X being removed. So let me give this definition. F of X, by definition, is F minus X, such that X belongs to F and this F belongs to the family. So since any well, why this is true? Why this is true? Well, any set from F intersects A1 union etc. union AS. So any set intersects this. And since any set intersects this, then if we think of this f of x as just the degree of x, then the sum of the degrees of all elements in A1 union AS is at least the cardinality of f. And then we just divide by the number of elements in A1 union AS, and then find out that the average degree is at least this quantity, and thus there is an element that has this degree, at least this degree. So maybe I should write here any set F from the family intersects A1 union etc. AS by the maximality of this collection, of the collection A1 etc. AS. Okay, great. So graphically, what do we have? We have this A1, AS, and then somewhere we have this element X, which has a large degree. But now we know that, well, first of all, f of x is a family of k minus 1 sets. That is, sets of size k minus 1, because we took sets of size k that contain x and removed x. And f of x has no r sunflower, because if it did, then we could have just added x back and got an r sunflower in the original family. So the cardinality of f of x by induction is at most f of k minus 1 r, which implies that the cardinality of f is at most k times r minus 1 times f of k minus 1 r, which is k times r minus 1. Now we substitute the upper bound, k minus 1 factorial times r minus 1 to the power k minus 1, and we get exactly the bound that we aimed for